Hello, everybody. So let's get started. My name is Jesus Camacho Rodriguez. I'm part of the engineering team at Hortonworks that works on Hive's optimizer, and I'm gonna give an overview on the optimization, on the work on that we have done on Hive's optimizer, and what is coming next. Yeah. So when Apache Hive came up already more than 8 years ago, the initial use case was batch processing. So you had read-only data. Your query language was Hive query language, which was SQL-like query language, but not really the standard. And you were running in MapReduce. But there is, like 3 years ago, a little bit longer, an effort started in the community to take Hive beyond its batch processing roots. This started with Apache Hive 0.10.0, January 2013. The latest release version right now is 2.1.1 that was released in December 2016. So we've come a long way. And the renovation of Hive was basically to improve 3 different axes. The first one was to improve its latency. So we wanted to move from batch processing to allowing interactive and sub-second queries. The second axis was scalability. So we wanted to scale, while reducing the query response time, we wanted to be able to scale to largest data sizes, so basically a petabyte scale. And also another axis was extending the SQL support. So we wanted to move from Hive query language to the SQL standard. So in order to reduce the latency, the execution time, there were multiple improvements that came into the execution internals. So first of all, we moved out of MapReduce, and then we supported multiple execution engines such as Apache Test or Spark. Some optimizations were introduced, such as, for instance, partition pruning. So basically, you will be able to read only that data that is relevant for the query itself. More efficient. There were improvements in the join execution algorithms. Vectorized query execution was introduced. So basically, you will have vector batches, and you will be able to execute analytical queries much faster. This also came with integration with columnar storage formats, such as Apache Orc or Apache Parquet. And finally, if you were in the previous talk about LLAP, so LLAP is GEA. It was introduced. If you were not there, basically what you will obtain, okay, many more things, but in this case, for the query latency, is you will get persistent daemons that will be able to execute your queries really fast by caching some data. Now, what is the motivation for the query optimizer? So what the query optimizer wants to do is to determine the most efficient way to execute a given query, right? And this can bring huge benefits for declarative language like SQL, where you are actually specifying what you want out of your data, but not how you want to obtain it. And this is especially true if the queries are generated by BI tools, because these auto-generated queries, usually they have many repeated patterns, and there are many opportunities for optimization. But the challenge with query optimization is that there is a trade-off between plan generation latency, so how long it will take for you to generate the execution plan, and optimality, so how optimal your execution plan will be. And why it is so important, the query optimizer, because actually the improvements in the internals that I mentioned before, we couldn't take full advantage of them without extending the optimizer. So you can have a very efficient join execution algorithm But if you get the ground join ordering, your queries, it will take ages for them to run. So yes. So let me give you a quick overview on the query optimizer in Hive. So before Hive 014, this is actually how we were compiling queries, right? So you would have your SQL query that will go through a SQL parser. You will generate some some abstract syntax tree. Then you will annotate that AST, and based on that, you would generate your physical plan that would be executed in MapReduce, right? Now, after Apache Hive 014, all these changes, because the logical optimizer is actually introduced, and it is powered by Apache Calcite. So what you will have now is that you will have your AST, but afterwards you generate a logical plan on which you will apply logical optimizations, and from there you go to a physical plan that will be executed. And with each new version of Hive since 014, there have been many improvements in the optimizer to make it more effective, so finding better plans, and also more efficient, so make it faster. And with each release also, we are shifting logic from Apache Hive to Apache Calcite. So this is an overview on the optimizer improvements since 014. Of course, I'm leaving some of them are not mentioned here. What is really important here is what you see with Hive 2.0. So suddenly 2.0 LLAP comes in, and suddenly it might take longer to plan the query than to execute it, because remember that with LLAP we can run in sub-second, and suddenly maybe you are planning the query for 1.5 seconds, 2 seconds, 3 seconds. So there is work that needs to be done, not only on improving or not only on getting the optimal plans, but getting them quick. Now, there are also other changes in, the optimizer is dependent on other parts of Hive. In particular, it's very dependent on statistics. So there have been also many improvements on the statistics in Hive in order to basically improve the collection, estimation, and retrieval of statistics. So first about collection, so faster computation of statistics, more statistics, so all statistics are stored per column and partition versus per table, and also automatic gathering, so you don't have anymore to analyze your tables. When you create your tables, you will be able actually to collect the statistics. Improvements in the estimation, so this is very important, because if we get grown stats estimation in the middle of a plan, we will get actually we might get the ground plan at the end, the ground execution plan. So there have been improvements in the selectivity on the estimates based on number of distinct values, minimum and max. And finally, the retrieval. There have been improvements on merging partition statistics, and there have been also multiple efforts to improve the metastore scalability by getting rid of the object relational management layer. So basically what this means is when you have many partitions, it's difficult to scale, because you will actually hit the metastore to try to gather the statistics, and yeah, basically it will not scale. So the ORML layer, what it tries to do is to introduce an abstract layer between the metastore database and Hive, right? And this was done basically so you don't have to program or to implement different integration logic for each of the databases. But this comes with a cost. This generality comes with a cost. That is that sometimes the ORM layer will emit queries that are not very efficient to the metastore, okay? So how people have tried to solve these multiple approaches, so one of them was, for instance, use Apache H-base to store the metadata, which is more scalable than other relational database management systems. And another approach has been to redesign completely the underlying schema for the metastore. This is something that was done by Yahoo And for some of their queries, it recorded improvements of up to 90% when it was actually retrieving the statistics. However, it is not clear whether that patch, as it is now, will go in or not. I think it has not gone it yet, because there are some discussions on whether this is the right approach, because this is very specially tailored towards one specific relational database management system, not a general approach. Now, logical optimization. So as I said, the logical optimizer is powered by Calcite. What is Calcite? Is a top-level Apache project. It doesn't have execution internals. What it does, well, it has, but it's not supposed to execute your queries. What it provides is a framework with relational algebra, so operators, transformation rules that are rules that will rewrite some parts of the plan into some new plan, and a cost model. And all these elements are extensible. So you can use ones that come with Calcite, or you can plug your own. It's usable standalone with JDBC or embedded. That is how most of the systems use it. And it has had a wide adoption by the Apache community. So there are, I think the last count is more than 10 projects that already use Calcite. So Apex, Drill, Flink, Hive, Kylin, Samsa, etc. Now, this is how the architecture of Calcite looks like. So you have multiple entry points. You can actually interact with the JDBC server. You could also use the expression builder that will help you create your operator expressions faster. You can also provide your own statistics for the metadata providers, your own rules. And in Hive in particular, we interact with the system at the lowest possible layer. So we will create operator expressions ourselves from Hive. We will provide our own statistics, and we also have some rules. We use part of the core rules of Calcite, but we also have implemented some rules that are specific for Hive. And then the query planner, of course, will take all this and will generate your optimized plan out of it. So the output is a relational expression, an optimized relational expression. So how this is done in Hive, it's a multi-phase optimization. There are both rule-based and cost-based phases, and till now there are more than 40 different rewriting rules that are enabled. So as you can see, there has been a lot of work going on there. You can see there many of them have to do actually with predicates, simplification of predicates, predicate pushdown. We'll see some of that with an example right now. So first of all, let me focus on an example of logical optimization, in this case, cost-based. So the most useful and typical one, join reorder. You've never heard of this. So basically, what the optimizer is capable of doing, that is very good for Hive, is we have an algorithm that can generate bushy join operator trees. And this is what this means is that instead of generating a left deep join tree where only one of the inputs can be a join, you can have join operators that can have joins in both their inputs. So this is very useful because that way you will be able to maximize parallelization. So you can actually execute in parallel these two joins, and then the result will be actually joined in the upper operator. So to see this with a practical example, let's say you have two star schemas, and you have two fact tables, sales and inventory. And then you have some dimensions tables, customer, time, product, warehouse, and these dimensional tables, when you join them with the fact tables, they will reduce the size of the fact tables. So now you have this plan that, as you can see, it will be bushy, and what happens is that on one side you have the sales fact table that will be joined with customer and time, and the size will be reduced, and on the other side you have inventory that is joined with warehouse and product. So when the results reach here, they will be really filtered, and your last join will have much less data to compute. So this is basically the kind of join reordering that that calcite can do. Now, so what about rule-based? So for rule-based, I picked up an example that is based on predicates. This is, it's a very clear example. They have to do with, what I want to show you here is how very simple rules can interact with each other in order to optimize the plan. So here we have 4 rules. One is predicate pushdown that will push the predicates as close to the scan as possible so we can filter the data faster. The other one is inference. So for instance, if you have a join and you are filtering the key for your join on a certain value, you can actually push the value to the other branch. Then propagation. So this is, if you know that a certain variable will have a constant value, you can actually propagate it through the plan. And folding, if you can actually pre-compute some of the expressions because they are based on, they basically contain all constants. So let me run very quickly through this example. We have a query that is joining address and sales and address on some column, and then you have a filter that you are saying that the country should be US and this certain ID, or the country should be US and this certain ID. And this is the query logical plan at the beginning, right? So you have your join, your table scan, your join, then your filter on top, and your project. And you start applying rules, rewriting rules. So first of all, you have predicate pushdown, so the filter suddenly will go closer to the address table. Now inference will kick in. So basically what we are saying here is if, you can actually infer additional predicates that should be true on this table scan. So in particular, we know that if in both cases the country should be the US, here it should be also the US, and here we can also include these conditions. So we infer additional conditions that will help us through the optimization phase. Propagation, so what I talk about, now you know that the ID should be equal, and you know here that the ID should be this value or this value. So we can infer it, we can actually propagate it to the other branch, and assume that this will be really useful. For instance, here now you only need to read records for 2 different IDs, and before you had to read all the data. What about folding? So you have that country is US, so you can actually replace the variable by the constant value, and now you can start folding. This becomes true, and another expression is true, so you can remove it. And now you have a repeated expression, you can remove it. So at the end, this is the final plan. As you can see, it will run much more efficient because before we were only filtering on one of the branches and with a more complex, not actually was with the same predicate. Now we will actually be able to filter both. Now let's move to physical optimization. So there are some parts of optimization that are done at the physical level. Physical optimization, what we want to try is to determine how the plan will be executed, and in particular, I mean which algorithms to use for each of the operators, for instance, for the join. And also, we want to take advantage about the information on partitioning and sorting of the data between operators, because maybe you can remove some of the repartitioning or sorting phases depending on the sorting order of the previous operations. And this is what I mean with removal of unnecessary stages. Right now it's completely done in Apache Hive, but as we tighten the integration between Hive and Calcite, we want to move certain things to Calcite, such as join algorithm selection. So very quickly, an example of physical optimization. So this is one that actually has been included in the latest, is included in the latest HTTP 2.6. It's already in Apache Master. So basically what we try to do here is to have a runtime decision to cancel a scan of records depending on the results of some subquery. This is very similar if you, or it is an extension if you have used Hive of dynamic partition pruning, but now you don't need anymore your you don't need that your data is partitioned anymore. And this equivalent in database management systems, this is equivalent to a semi-join reduction optimization. So we have this query that joins sales with time based on a certain ID, and then we are filtering by year and quarter. So as you can see, statically, we cannot infer which ID will be joined. So this is the physical query plan. So you have scan, the filter, and then the reduce sync, some join, and some scan on the sales. And what we'll do is we compute till the keys of the reduce sync that will be actually transferred to the scan. And then there are some internal data structures based on Bloom filters actually that will be able to filter these records very quickly so the join size is reduced. This is done at runtime and dynamically. Okay, optimizer performance. This is, I'm gonna do it very quickly. What I did yesterday basically is to take the latest Apache Hive release and to run some numbers, because obviously I knew that if I disable the optimizer, I was gonna obtain much better results with the optimizer on, right? But you can see that even though we have introduced, this was not disabling all the improvements to execution internals, even with those internals going in, if the optimizer doesn't kick in, there is a lot of difference in performance. We are talking from 10% up to 90%. Depending on your query, of course. Some queries will benefit more, some queries will benefit less. If you want more about performance, I'm not going to talk anymore about it. There were several talks that already focus a lot on numbers, but there will be some updates on Hive performance within a few weeks in the Hortonworks blog, so you can stay tuned and check for that for more numbers. And finally, road ahead. I think I've gone a bit quickly, but I have also some material here. So this is things that are being developed right now. They are not ready yet, so this is really new, just checking into master. So one of them is an extended cost model. So I was talking about the statistics, I was talking about join reordering, that is a cost-based optimization. Right now that cost-based optimization is done based on a cardinality cost model, and we want to go beyond that. So we want to have basically a cost model that reflects better the actual execution cost. So this extended cost model, what it does is to take into account CPU and I/O cost for the operators. It is dependent on the execution engine, of course, because some engines will execute some operations in a more efficient way than some other. That's also a bit maybe preventing from adopting it right now, because we have to make sure that there are no regressions, and we will have to tune it. Up till this moment, there is only it only exists for Apache test. Well, these are the tuning parameters, so you will have to give some cost to your CPU, atomic operations, local disk byte read and write cost, HDFS read and write cost, network transfer. So once you give these parameters, then you will get the real cost of the expressions. And the good thing about introducing this cost model and the interaction with calcite is that it will allow joint algorithm selection in Apache calcite. That is something that we really want to do, to see also how it interacts with the other rewriting rules. Another work that is ongoing right now is materialized view support. So probably many of you are already familiar with materialized views. A materialized view contains the results of a query, and they are very useful because it will allow you to pre-compute some results, and what we want to implement is or what we have already implemented partially is automatic rewriting. So you will have your queries coming in, and you have your views, and then you will rewrite your queries to be answered from your materialized views. Good things. One of the good things is that this automatically benefits from LLEP. since a materialized view is nothing more than a table, so it can be cached. And also another advantage is that you can use other systems to store the views. So I don't know if some of you were in the talk this morning about Druid, but the goal here also is to store data in Druid as a materialized view in order to speed up the response for the query workload. And yeah, there are also powerful side effects. One of them, I'm talking the whole time about the statistics, so one of them is that you will get precise statistics, because if you have the statistics for a given query or subquery and you identify that this subquery is part of this query, well, you already have all the statistics computed for this subplan. So very quick example of what is already there. So assume that you have this simple table in Hive. You have an ID, name, unit price, and discount. And what you can do right now already is to create a materialized view like that. You can enable it or disable it for rewrite. So this is something that that you should add if you want to enable it for the rewrite. And then here you define the query for your view. So in this case, we are just doing a simple selection of ID discount where the discount is greater than 20%. Okay, so this is your view, and now it is in the system. So now, when a query comes, you will have the query plan. So for instance, in this case, it's asking for ID discount from the same table with discount greater than 30%. So you can observe that this is the query plan. This is the materialized view plan. And what you can see here is that the query results are contained in the view itself. So the rewriting will kick in. The rewriting is just implemented as a rule. It's a rewriting rule. And you will end up answering your query from the view. So you will do a scan over the view, and you have to add the additional filter because in the view we had a store discount greater than 20%, and here we have discount greater than 30%. This is the kind of containment that we check. Currently, it's not being merged to master, but we support, or we plan to support project, filter, join, aggregate, and scan operators. We have to still do some improvement for the early prefiltering of irrelevant views because rewriting is very expensive, view-based rewriting. So we want to discard the views that are not useful as soon as possible, so we don't enter even the rewriting. So there are some improvements that are being made there. And what is ahead? Okay, so allow partition materialized views. This is something that we don't support right now. And also we will need to explore the materialized view maintenance. So once you have created your view, how can you actually keep it up to date with your tables? We plan also to introduce some parameter, some time window for valid automatic rewriting. So if you pass this time window, you will not trigger the rewriting. So yes, this is, so to conclude, this is what I show you. I show you the improvements over the last 3 years that there have been in the optimizer to improve its effectiveness, its efficiency. There are multiple contributions to both projects, to Apache Hive and Apache Calcite. And we think that there is a very interesting road ahead for both communities. There is a lot of work going on, query decorrelation, materialized views, query factoring, plan caching, parameterized plans, and many more coming. So if you want to get involved, just check the issues of these projects. And yeah, finally, acknowledgments. I mean, this is a work of really a lot of people at Hortonworks and in the community. So yeah, thanks to all of them, Ashutosh, Julian, Penchen, Vinit, some people that are not working on Hive anymore, John, Harish, and many others. And also to Julian for sharing some slides of previous optimizer talks. So that's it. Thank you. And questions? Yes? What about Hive on Spark? Hive on Spark. So So, I mean, everything that I have, except the extended cost model, everything related to optimization, basically, it will run on the same way on Tess or on Spark. You know, the whole optimization process, as I said, the cost model is cardinality based. So this will run the same way. There are some physical optimizations that might not run on Spark. To be honest, I don't know the current status of the integration. I don't know if it's very well supported. We've been doing a lot of work on tests. But yes, there are many things that I have talked about, the rule-based optimizations, the cost-based for the joint reordering that is independent from the execution engine. So it will still benefit from it, yeah. No more questions? You fell asleep? Yeah. It was a heavy talk at this time in the day. Yes?
But if I run Spark, let's say Spark shell and use a Hive context, does this optimization now work, or does it work on Spark then?
I don't get the question.
That's using Spark's optimizer if you do that.
Okay.
Okay.
It's just using Spark's.
Okay.
Context could have been Hive as well.
No, I think it's just using the metadata for Hive tables.
Okay, so I'll be around if you have any more questions, you want to talk about anything related to this, just ping me, okay? Thank you, everybody.